One important task in symbolic logic is showing that two statements are logically equivalent. In other words, that they mean the same thing. And I want to start by taking a look at an example of just writing out a few compound statements and trying to determine their meaning. So if we let P be the statement, I have long hair, and Q be the statement, I have a beard, let's start by writing out negation P and negation Q. So if P is I have long hair, then its negation would be I don't have long hair. And then the negation of Q would be I don't have a beard. So this statement would read I don't have long hair. And I don't have a beard. Now, let's think about what this statement is saying and what cases would it be true. So, again, this is a conjunction, the and statement. It's saying both of these things are true. So, I don't have long hair and I don't have a beard. In other words, I have neither long hair nor a beard. Okay, now let's compare that to if we have the negation outside of the conjunction in a set of parentheses. So this is the negation of the statement, I have long hair and I have a beard. One way to write that out directly would be it is not the case that, and then I'm going to use a comma to signify that the statement P and Q, I have long hair and a beard, is in parentheses, so it is not the case that, comma, I have long hair and a beard. Now, grammatically, written out this way, it looks a little awkward. We wouldn't really say it is not the case that I have long hair and a beard, but that is the simplest way to directly translate this from the symbolic statement into the written statement. Now let's think about what this is actually saying. It's saying it is not true that I have both long hair and a beard. In what cases would that statement be true? So if I say it's not true that I have long hair and a beard, well, if I had long hair but no beard, this statement of I don't have both would be true, right? Basically, this is saying I don't have both long hair and a beard. So if I'm missing the beard, this statement is true. If I'm missing the hair, this statement is true. If I don't have either, this statement is true. The only time this statement would be false is if I have long hair and a beard. Then this statement would be false. So how does that differ from the first statement? The first statement is saying I don't have long hair and I don't have a beard. So that statement is saying I don't have either. The second statement is saying it's not the case that I have both. So that's saying I don't have both. Okay, so it's very, kind of tricky distinction here, but again, the first statement is saying I don't have either. The second statement is saying I don't have both. Okay, and let me just write that out in green. So I don't have either. Versus I don't have both. So the first thing this shows us is that the negation can't just be distributed, right? We can't just take this negation and distribute it to P and Q to get this statement here because they don't mean the same thing. Again, one says I don't have both, the other says I don't have either. But let's take a look at this statement, negation P or negation Q. So this would be I don't have long hair. That's the negation of P. Or I don't have a beard. Okay, so what does this mean? This is saying either I don't have long hair or I don't have a beard. In other words, I don't have both. I must be missing one or the other. I don't have both, which was the same as the second one. Okay, so again, if we read through that again, the statement, I don't have long hair or I don't have a beard, it's saying I'm missing one or the other, so I don't have both. So we see here that this statement, negation P or negation Q, was actually the same as this statement, the negation of P and Q. Now, the strength of symbolic logic is when we're dealing with the actual written statement, things can be very confusing. Trying to determine the meaning of something like this can be, well, a little confusing. And Logic breaks these things down into symbols and variables and gives us an abstract way to analyze them. Now, dealing with abstraction is usually more difficult, but as we're seeing here with the statement, sometimes the words get in the way. And so being able to look at something like a truth table, for example, that doesn't care about what the actual wording of the statement is, actually can be, easier. Okay, so the second and third statements here we say are logically equivalent. And as a definition, sorry, not two sets, I'm going back to set theory here, two statements rather, are logically equivalent. All right, there, we'll straighten that up. So two statements are logically equivalent if they have the same truth value in every case. That is, that their truth columns are equal. And there's a couple different notations here. We'll use the triple bar just like set equivalency, or a double arrow. Either one, you'll see in different scenarios. Okay, so what we just said was that, again, going back to this example here, the negation of P and Q was logically equivalent to the negation of P or the negation of Q. And what we want to do is show that's true symbolically, and that means it would be true no matter what the statements are, whether we're talking about beards and hair, or, it raining on a certain day of the week, or certain breeds of dogs being prone to biting. So we want to do this using a truth table. We're going to look at the truth table, and if we make a column for each of these statements, then if we show those truth columns are the same, then the statements must be logically equivalent. So we have two simple statements, P and Q, so that yields 4 cases. So we'll set up our truth table the same way we have been for two simple statements. Now, I need to build the negation of P and Q, so I'll start by doing P and Q. And remember, this is only true in the first case, where P and Q are both true. And then we'll negate that, which would swap all the truth values. So instead of true, false, 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 we would have false, true, true, true. Now, to build negation P or negation Q, we would need a negation P column and a negation Q column. And then from there we can compare them with the OR. So negation P just flips P. Instead of true, true, false, false, we'd have false, false, true, true. And instead of true, false, true, false, we'd have false, true, false, true. All right, and then we have negation P or negation Q finally. So that's looking at the two columns we just made, and if either of them are true, then the OR statement is true. So if we look in the first case, they're both false, so the OR statement is false. But in each other case, at least one, if not both of them, is true, and therefore the OR statement is true. Oops, sorry, that first case I said false and then wrote true. Sorry about that. Okay, so now if we compare our two columns for the negation of P and Q versus the negation of P or the negation of Q, we see those columns are the same, false, true, true, true. And therefore the two statements are logically equivalent. Now this equivalency is actually something that we've seen before. Our next theorem is what we call De Morgan's laws, and you may recall De Morgan's laws for set theory that had to do with taking the complement of a union or an intersection. The complement of the union or the intersection is actually related to negating the and or the or statement. And so that thing that we just proved here, let's see, that was actually the second one, is one of De Morgan's laws. It's basically saying that the negation can be distributed in to the conjunction, but we flip from conjunction to disjunction. And the same is also true for the disjunction. And just recall when we were talking about set theory, we had something like A union B complement was the same thing as A complement intersected with B complement. That is, we could distribute the complement by reversing the union to the intersection. And so same Augustus De Morgan is what this theorem is named after. Same concept either way between set theory and logic. And this is one of the many links between set theory and logic, where when we get some concept from set theory, oftentimes we can find its corollary in logic. Okay, so let's look at another example of showing logical equivalency. Suppose I wanted to prove that the negation of, if P then Q, is the same thing as negation Q and P. Now, just to reiterate sort of the power of truth tables and doing this symbolically, if I tried to put actual statements in there, for example, if it is Tuesday, then it is raining, then the negation of that would be saying it is not the case that if it is Tuesday, then it is raining. And the claim here is that's the same thing as saying it is not raining and it is Tuesday. I haven't written all this out because it gets very confusing very quickly, but essentially what we're trying to do is say that it is not true that if it is Tuesday, then it is raining. It's the same thing as saying if it is not raining and it is Tuesday. Who knows if that's true or not, right? Well, we will in a moment. So what we're going to do is build the truth table for both of these statements and show that their truth columns are the same. 2 simple statements, 4 cases. Then we want the negation of if P then Q, so we'll take a look at the conditional, if P then Q, and then we can build a column for its negation. Again, the conditional, true, false, true, true. So its negation would be false, true, false, false. Then we want a negation Q and P column, so let's start with a negation Q, which Q reads true, false, so its negation reads false, true. And then finally we can put that together with P. And, excuse me, so this is only true if the P column and the negation Q column are both true. Which case 1, that fails because negation Q is false. Case 2, they're both true. Case 3, we have a false in both cases. And case 4, we have a false for P. So we have false, true, false, false. And notice that is the same as the negation of if P then Q column that we already built. So when we're asked to find or to show or to prove that 2 statements are logically equivalent, well, all we're going to do is just build a truth table and show that their truth columns are the same for each case.